All right, let's talk about concurrency in Go. It's probably the feature you've heard the most about. It's incredibly powerful, but it can also be a little tricky. So today, we're going to break it all down. We'll look at the common mistakes people make and the patterns you absolutely need to know to get it right. So you type those two little letters, Go, and hit Enter. What's really going on under the hood? It feels like magic, right? Well, you're unleashing a ton of power, but you've also got to be careful. We're going to dig into what Go actually promises you, what hidden traps can trip up even the pros, and how to use the right patterns to write code that's not just fast, but also safe.
Okay, first up, Section 1, the core problem. And it all comes down to something called the visibility guarantee. So let's start with a really simple question. Imagine one Goroutine sets a variable, say x equals 10. When does another Goroutine see that change? You'd probably assume it's, well, immediate, right? But here's the shocker. It's not. There's absolutely no guarantee. See, to make your code run crazy fast, modern CPUs and compilers are constantly shuffling instructions around and caching data. And without some ground rules, this optimization would just create total chaos for our concurrent programs.
And to prevent that chaos, Go gives us a rulebook. It's called the Go memory model. Now, you don't need to read it cover to cover, but you do need to get this one core idea it introduces, a relationship called happens before.
And this is really the golden rule of Go concurrency. If you can prove that one event happens before another, then you have a guarantee that the second event will see all the effects of the first. But if you don't have that happens before link, all bets are off. No guarantee. The runtime can do whatever it wants, and that's where those really nasty, hard-to-find bugs come from. You know, a great way to think about this is sending a letter. So, you write the letter, that's like writing to a variable. Then you put it in the mailbox. That's our synchronization event. Your friend then gets the letter and reads it. The key part is the mailbox. That's the thing that creates the happens before relationship. Putting the letter in the mailbox happens before your friend takes it out. It's that simple. So, what are these mailboxes in Go? Well, they're the synchronization tools you're probably already familiar with. Sending on a channel happens before the receive is complete. Unlocking a mutex happens before the next lock succeeds. Even a sync.once call finishing happens before any other call sees it's done. These are the mechanisms that give us our guarantees. Okay, on to Section 2. Let's see what happens when we forget these rules. We're going to look at two super common traps, Goroutine leaks and messed up loops.
First up, the Goroutine leak. What is it? Think of it like this. You hire a worker, but you forget to tell them when they can go home. They just stand there forever, waiting for instructions that never arrive. That's a Goroutine leak. It's a Goroutine that's stuck, never finishing, and just eating up memory for no reason.
And how does this usually happen? It's almost always a Goroutine that's blocked waiting to read from a channel. But no one is ever going to write to that channel again. The sender's gone, the work is done, but this one poor Goroutine didn't get the memo, so it just waits forever. So how do we fix this? The classic, idiomatic Go solution is called the done channel pattern. It's brilliant. You basically pass another channel into your Goroutine, and its only job is to signal, hey, it's time to pack up and go home. And a cool pro tip, we often use a channel of empty structs, a chan struct, because it takes up zero memory. We don't need to send any data, just the signal itself. And here's how you put it into action. The magic is the select statement. It lets the Goroutine listen to more than one channel at the same time. So in its loop, it can wait for work on the jobs channel, or it can wait for a signal on the done channel. Whichever one comes first wins. So when the creator of the Goroutine closes the done channel, that case immediately unblocks and the Goroutine can exit its loop and shut down cleanly. No more leaks. All right, let's talk about the other big trap. I swear this one gets everybody at least once. It's what happens when you try to start Goroutines inside a for loop. If you're not careful, the result you get is, well, probably not what you expected. So here's what's going on. When you run a loop, there's only one loop variable, say I. Its value just gets updated on each trip through the loop. The problem is, your Goroutine doesn't grab the value of I at that moment. No, it grabs a pointer back to I. So by the time your Goroutines actually get a chance to run, the loop is long finished and I is sitting at its final value. And that's the value all your Goroutines see. But the fix, luckily, is super simple once you see it. Instead of just using the loop variable from the outer scope, you pass it in as an argument to your Goroutines function. This one simple change makes all the difference. Why?
because now each Goroutine gets its very own private copy of the value from that specific loop iteration. Problem solved.
All right, section 3. We've seen the problems, now let's talk about the solutions. We'll look at some idiomatic Go patterns for communication and control.
If you remember one thing about Go concurrency, make it this quote. This is the whole philosophy. Instead of the old way, where you have a bunch of threads fighting over shared data and you use locks to keep them from crashing into each other, Go says, don't do that. Instead, let one Goroutine own the data, and if another one needs it, communicate, send it over a channel. It's a much cleaner, often safer way to build things.
Now, Goroutines are cheap, but they're not free. You can't just spin up millions of them without thinking. So sometimes you need to limit how many are running at once. Here are 3 popular ways to do it. The simplest is just using a buffered channel as a semaphore. It's a quick and dirty way to control access. A more structured approach is the worker pool pattern, where you have a fixed number of workers pulling from a job queue. And for more complex stuff, especially when you need great error handling, the error group package is fantastic. It handles a lot of the tricky parts for you.
Okay, final section. Let's get into some of the advanced stuff. This is the expert's edge, the details that really separate the pros. We'll look at why Go is so fast and some power tools you should know about even if you don't use them every day.
First, let's talk about memory. A brand new Goroutine costs you about 2.8 kilobytes. That's tiny. To put that in perspective, a traditional OS thread in another language might start at 1 or even 2 megabytes. That's 1,000 times bigger. This is why you can have hundreds of thousands, even millions, of Goroutines running in a single Go application. They're just ridiculously lightweight.
And it's not just memory, it's speed too. Switching from one task to another, a context switch, is way faster for Goroutines. Why? Because the Go runtime manages it all in-house, without asking the operating system for help. As you can see here, we're talking about a difference measured in nanoseconds. It's just a completely different league of performance compared to old-school OS threads.
Okay, and here's a real power tool for your toolbox, runtime.lockOS_thread. Now, 99.9% of the time, you will never need this, but it's good to know it exists. It lets you pin a Goroutine to a specific operating system thread. This is sometimes required when you're calling out to C libraries or working with GUI frameworks that have strict thread requirements. But, and this is a huge but, use this with extreme caution. You are actively fighting against the Go scheduler, and you can really hurt your performance if you misuse it.
So let's wrap this up with the key takeaways. Number 1, memory writes aren't instantly visible unless you use synchronization. You have to establish that happens before relationship with channels or mutexes. 2, every Goroutine you launch needs a clear exit plan to avoid leaks. And 3, when you launch Goroutines in a loop, always pass the loop variable in as an argument to create a copy.
Look, knowing these patterns is a huge step. They give you the power to build incredibly fast and scalable software. But the real question is, are you applying them correctly? True safety, true mastery doesn't just come from knowing the tools. It comes from deeply understanding why they work and being disciplined enough to use them correctly every single time.